Alright, welcome everyone to the stream on cardinality. This is where discrete math gets a little bit more challenging. I think we all felt that to one degree or another. But we are going to use our ideas on functions in the previous stream. If you want to check it out, feel free to check that out. And we are going to use injections, surjections, and bijections to talk about comparing the sizes of sorts between sets. So we first want to establish some useful properties about surjections and injections, and we'll find a very useful property on bijections as a result from that. We'll use bijections to talk about the sizes of different sets, and that is how we're going to argue throughout this live stream. So let's start off with the first question on the composition of functions. If the functions are surjective and injective, what kind of properties should we expect? So suppose we have functions f and g, and we know that both functions are surjective. I think it's a reasonable claim that the composition ought to be surjective as well. But let's go ahead to actually establish that claim. To establish this claim, we're going to start off with the definition of surjection. And what that means is that we are going to regard what exactly is going on here. Well, G circle F is gonna go from A to C because F goes from A to B, G goes from B to C, so G circle F will go from A to C. Which tells us that we can go like this. To establish surjectivity, we need to take every output and show that there is at least one input that's connected to the output. So we'll fix y in C because that's the output with respect to G circle F. And we want to find an input. With the property that G circle F of the input gives us the output. How should we go about this process? The first thing to note is we can't really do much with G circle F directly because we know nothing about G circle F. We do know, however, that G circle F is made up of F and G, and we do know that F is surjective and G is surjective as well. Now, Y is in C, and C is the collection of outputs of G. So we know that G is surjective, which means that every output has at least one input. So since G is surjective, we can find, well, this is kind of awkward, we'll call this C in C, right? Since G is surjective, we can find a B in B such that G of B equals to C. That's because G is surjective. For the output C, you can find an input B such that G of B is C. But here's something interesting about B. B is an input with respect to G, but an output with respect to f. And what that means is that if B is an output with respect to f, and f is surjective, that means we can find an input. So, since f is surjective, there exists an input A with the property that f of A is equal to B. And now we can sort of combine some of the information here in order to get an expression that looks almost like what we are looking for. So let's combine these two equations. We can plug the B into the G, and we're gonna get G of f of A equals to C. But G of f of A is precisely G composite of f of A. That's what it means for a function to be a composite function. You plug one into the other. In other words, for any C, we have found an input A such that G circle f of A equals to C. And that actually helps us establish that G circle f is surjective. So that's a pretty neat result, if I could say so myself. It's pretty cool that if you take two surjections, you get another surjection. A natural question to ask as a follow-up is what happens if f and g are injective? Is G circle f also injective? And we would like to think of it this way. If every input, or rather, if every output over here has at most one input, and every output over here has at most one input, then if we take an output here, we'll get at most one input here, and for any of these guys, there's at most one input here. So intuitively, we would think that for any output, there is at most one input, and most likely, we would think that this is a true statement. Turns out that it's gonna be true as well, and we can go ahead to prove this result. To go about proving this result, we're going to fix two input values with the property that they have the same output. And our goal is to show that these inputs must be one and the same. This tells us that every output has at most one input. And with that, how do we proceed? Once again, composite functions don't tell us a lot, but we can break it down as a function inside another function. So let's write out the left-hand side as g of f of a1 and the right side as g of f of a2. And something remarkable happens here because we know that g is injective. And if g is injective, that means every output has at most one input, which means that the two inputs here must be the same. So we write it this way, and let's justify it because g is injective. But if f of a1 equals f of a2 and f is injective, then the inputs must be equal to each other as well. And that tells us that a1 must equal to a2. This helps us conclude that g circle f is injective. And that's pretty cool. So that's some pretty cool results here. Let's go ahead and clean up the board and establish one more result which will be really important for the rest of the questions that we will be solving. So we have proven that if f and g are both surjective, the composite must be surjective, and if the functions are injective, then the composite has to be injective as well. We have a question here, how to prove that a given planar is 3 colorable. We won't be doing graphs today, we'll be doing cardinality. We'll be doing graphs eventually, and I'm going to have to think about that question before I can give a response here. I have no idea. In fact, I think we have a counter example to this result, right? So let me very quickly answer this. I think there is a counter example because we can find, we should be able to find one which is not 3 colorable. I think I'm very curious to see if this works. I believe this graph is not 3 colorable, right? But we need to define 3 colorable properly before we can actually properly answer the question. But I think this actually answers your question. This is a counterexample. Right? This is probably not 3 colorable. But it is 4 colorable, right? That's the famous 4-color theorem in graph theory. Every planar graph is 4 colorable. And I'm not going to prove that because that takes quite a lot of effort. So there is that. So an interesting result is what happens if the constituent functions f and g are bijective. Would the composite be bijective as well? I mean, surely if it's bijective, it satisfies all these nice properties, we would like it to be bijective. Let's just check that this is a legitimate conjecture. So here's the claim. If f and g are bijective, then g circle f is bijective. Let's proceed to prove this claim. And here's how I'm going to prove it. I'm actually going to draw some tables just to highlight how the proof is going to work. So here's a table. And here's the proof. Since f is bijective, well, f is bijective, and g is bijective because that's what the question tells us. G and f are bijective. Since f is bijective, it is surjective and injective at the same time. Since g is bijective, it is also surjective and injective at the same time. So now we have f and g being surjective, but we've seen that if f and g are surjective, then g circle f must be surjective. And similarly, we see that f and g are injective, so g circle f must be injective as well, which means that g circle f is surjective and injective at the same time. And therefore, g circle f is bijective. So a cute little proof here using just some logical arguments in a rather unconventional presentation, but the proof arises from converting all of the tick marks, if you would, into words. That should be fine. A natural question to ask is what happens if we were to swap the statements. Currently, if the constituents are surjective, the composite is surjective? Can we go the other way around? Let's clean up the board and present the question and present our answer. So we have this question. If instead we now know that the composite is surjective, do we automatically have that the constituents are surjective? A usual rule in math, not a rule but just a rule of thumb if you would, is that if a statement goes in one direction, it's unlikely to be true in the other direction. So we probably think it's probably not going to be the case. And here's a quick proof as to why that's the situation. So here's my claim. My claim is that it's going to be false. That's my claim. And here's my proof that it's false. We're going to define a function in the following manner, or two functions in the following manner. Here's the function we're going to define. F is going to go from 1 to 2, 3 in this following manner. 1 gets connected to 2. It's a function. And G is going to go from 2, 3 to 4. And it's going to go in this manner. Both items are going to point to 4. It's still a function. So G circle F is surjective because every output, the output 4, has an input 1. So G circle F must be surjective. However, F is clearly not surjective because it can't hit both items inside the middle set. To be more precise, let's use A, B, and C to represent these sets. So here's a counterexample, and therefore, it's not always true. Now what's interesting is that we might not have both functions F and G to be surjective, but even in the diagram, we can see that G is surjective. And if we think about it, if this whole thing is surjective, that means every item in here has, well, every output in here has an input in here, and every input in here has an output in here. So therefore, this output will be an input for this particular output via the function G. Right, so let's sort of think about that a little bit more. For this output, because G circle F is surjective, we're going to get an input here. Now this input is going to have an output because F is a function. So it turns out that this output is going to be the input for this output via the function G. So we're sort of suspicious that, wait a minute, if G circle F is surjective, is G surjective? Turns out, sounds about right. So let's claim that if G circle F is surjective, then G is surjective. So we might not have both functions being surjective, but we do have one function that will be surjective. That's the claim. So let's go ahead to prove this claim. Well, what does it mean for G to be surjective? How do we establish this claim? We need to fix an output C. And our goal is to find an input B. And how do we go about doing that? Let's go with that idea that we had just now, because that's going to be an interesting idea for us. We fix C inside the output space. Since G circle F is surjective, there exists some input A, because G circle F, the inputs, the domain is A, such that G circle F A equals to C. We can write this as G of F of A equals to C. And F of A looks pretty suspicious, right? F of A looks suspicious. Well, but does F of A exist? It has to, because F is a function, right? So since F is a function, there exists, in fact, it's a unique B in B such that F of A equals to B. Every input must have exactly one output. And therefore, we can write this as G of B equals to G of F of A, because B equals F of A. But G of F of A, we've seen just now, evaluates to C. And that is precisely the conclusion that we were trying to obtain. And we've done this for surjections, but can we do this for injections? Let's clean up the screen and set up the question and go ahead and answer a similar pair of questions. So here's the question. If G circle F is injective, is it true that F and G are both injective? We've proven before that if F and G are both injective, then the composite must be injective, and in general, the converse is not going to hold. Turns out that the same counterexample that we had for the surjective case works here. But let's just recap what that looks like. Where we will define a function f from the set containing 1 to the set containing 2, 3. And we'll define a function from the set containing 2, 3 to the set containing 4. And we see that G circle F is injective because every output has at most one input. And yet G is, well, G is not injective, right? The output 4 has two inputs, 2 and 3. And thus, we can conclude that that's not true either, right? The converse is not true either. But we do notice that F is just one piece over there, right? F is just one. And that's rather fascinating. What's sort of going on here? What if F is injective? And here's the idea, right? So let's take any output over here, any two outputs. Let's just say the output 2. The output 2, we suspect that it has at most one input in A. And if you plug it through G, you're going to get another item because G is a function. And this new item lies in C. But the item in C, because G circle F is injective, has only one input in A. That's sort of the idea behind the proof, but let's first make the claim that if G circle F is injective, then F is injective. Let's go ahead to prove this claim. This is a rather fascinating claim to establish. How do we show that F is injective? We will need to fix two items in the input space. And we want to prove that if the outputs are the same, if FA1 equals to FA2, then A1 must be equal to A2. Let's write it in symbols as follows. And let's write down our goal. Our goal is to show that A1 equals to A2. And how do we start? Well, because f of A1 equals to f of A2, if you apply the function g on both sides, it's still going to be the same output because the same input should give you the same output. So, since g is a function, if we apply g on both sides, we will still get equality. But once we see a function inside a function, we probably want to use the composite to our advantage. So let's go ahead to do just that. And now we have g circle f of A1 equals to g circle f of A2. But g circle f is injective, which means that every output has at most one input. So in other words, if the outputs are the same, the inputs must be same. But if the inputs are the same, we get A1 equals to A2. And that's that. That's how we show that F is injective. Because if FA1 equals to FA2, if the outputs are the same, the inputs must be the same. So, turns out that even though we don't get the full converse, we call this a partial converse, and we do get some similar results. So with these ideas in mind, we want to recap the very useful result that we have proven just now. That is, if the composite is bijective, then, or rather, if the constituents are bijective, the composite is bijective. And using this result, we can go ahead to prove several claims about sets having the same cardinality. But let's take a look at that in just a moment. So we've previously proven that if the constituents are bijective, the composite is bijective. This is going to help us prove some results about cardinalities of sets. So here's our first claim. In fact, before I write the claim, let's just create the setup. We'll let A, B, and C be sets. And our first claim is that A has the same cardinality as itself. In an informal, imprecise way, Same cardinality means same size. I mean, it kind of makes sense. A set should have the same size as itself. But what do we mean by same size? We need to be precise about the idea of same size. And we have a definition in terms of bijections to help us do just that. We will say that two sets have the same size if there is a bijection from one to the other. Well, more precisely, let me rephrase the statement. We say that the set S has the same cardinality as the set T if we can find a bijection from S to T. And this is how I'm going to abbreviate the expression. I'll just say there exists a function from S to T that is a bijection. We'll say that S has the same cardinality as T if you can find a bijection from S to T. And using this definition, it kind of makes sense that A has the same cardinality as itself. Just do nothing, right? Take every item and just return the same item. That's going to be the same cardinality, or not the same cardinality. It's going to be a bijection, but let's make this precise. So let's prove it. We'll define the identity on A, which is the do nothing function. And just to recap, it's a bit like this. And we can check that this guy is a bijection. We can check the identity is a bijection. It's kind of obvious, like, duh. But let's just check it out, just to be safe. So we claim that it's bijective. Let's check that it is injective. Well, we claim that it's bijective, so let's check that it's surjective and then injective. So it's bijective. To show that it is surjective, we need to take any item in the output space and find an input in the input space. So we're gonna fix A inside A, and we'll choose some input so that the identity on the input equals to A. Well, the identity is the do nothing function, right? So what will produce A? Well, it's just A. So I'm going to choose A in A so that identity of A equals to A. Therefore, the identity is surjective. And for injectivity, we need to fix A1, A2 in A. And we will suppose that the outputs are the same. Then we need to check that the inputs are the same. But by the definition of identity, it's kind of obvious. So, but let's just do it properly. Then on the right side, the identity on A2 is just, well, A2. And the identity on A1 is just, well, A1. So the identity has to be injective as well. Since the identity is surjective and injective, it's bijective. And since we have found a bijection from A to A, we can say that A has the same cardinality as A. And there's that. So with this definition of there being a bijection, it's not too challenging to show quite a few interesting properties. Let's clean up the board and we're gonna show a few more same cardinality results. Here's our next cardinality result. If A has the same cardinality as B, then it stands to reason that B has the same cardinality as A. Kinda makes sense. So how do we prove this result? Let's just start from the first result and work our way to the, well, let's start with the left side and work our way to the right side. So we'll suppose that A has the same cardinality as B. And that tells us that we can find a bijection from A to B. Maybe it's not too easy computationally, it might take a little bit of effort, but if we know they have the same cardinality, we know that there is a bijection from one to the other. And something interesting about this result is the fact that if the function from A to B is a bijection, the inverse will also be a bijection, right? The inverse is also going to be a function that it is injective and surjective, and therefore the inverse is going to be a bijection. Perhaps you can prove that as an exercise. And if F inverse is an injection from B to A, what am I saying? If F inverse is a bijection from B to A, then B must have the same cardinality as A by definition. And that's kind of a pretty intuitive result that we have there. Let's go ahead to clean up the board and prove one more result about cardinalities between two sets in general. And here's our next result which we want to prove. We want to prove that if A has the same cardinality as B and B has the same cardinality as C, then it stands to reason that A has the same cardinality as C. I mean, it sort of makes sense. If A and B has the same size-ish, and B and C have the same size-ish, then A and C have the same size-ish. So, how do we prove this? We start from the left and work our way to the right once again, and let's just see what we get. So let's start with the left side. So since A has the same cardinality as B, we can find a bijection from A to B. And likewise, from B to C, we can find yet another bijection because B has the same cardinality as C. And now we have F going from A to B and G going from B to C, and both are bijections. So we've proven before, in the previous part, that if the constituents are bijective, so is the composite. That's a pretty cool fact right there. So what we have here is that G circle F going from A to C is bijective. So just a quick recap of how to visualize the composite function. We'll go from A to B via F, B to C via G, and we can go from A to C via G circle F. So if G circle F is a bijection from A to C, this tells us that A has the same cardinality as C. And we have, in a sense, similar results pertaining equivalence relations, but we need to make that a bit more precise in the future, so we probably won't really touch it, but it satisfies some of the similar properties. Now with that, we can actually go ahead to test the waters a little bit and try to work with using bijections and cardinalities to derive certain results. Now, suppose we know that two sets A and B have the same cardinality. We want to go ahead and prove that if A is finite, then B is finite and vice versa. And it's kind of obvious. It's like, yeah, obviously, right? If A is finite, then and A and B have the same cardinality, then surely they have the same number of items and B should be finite. But once again, we need to prove this using the definition. And what do we mean by A being finite? While it may seem a bit obvious, we have a technical definition for this. We say that a set A is finite if we can find a bijection from A to a finite collection of natural numbers. So we have this definition of a set being finite, and we probably want to go ahead to use that definition. We're going to prove one direction and leave the other direction as an exercise. So we're going to prove this particular direction, and the reverse direction is almost the same. So we'll suppose A is finite. In fact, even before we prove any directions, we can actually state a fact of life from what the question gave us, which is the fact that A and B have the same cardinality. So right away we have a bijection from A to B. And now we can suppose that A is finite. What does that tell us? It tells us that there is a bijection from A to some collection of natural numbers. So let's write it this way. Now, how is that supposed to help us? Let's maybe draw a picture on the side to sort of visualize the situation. We know that A and B are bijective, and A is bijective to a collection of natural numbers. So in some sense, we want to argue that B is bijective to this, well, not B is bijective. There is a bijection from B to this set of natural numbers. And the key trick is the fact that F inverse is a bijection. Because F is a bijection, and so if we go from B to A via F inverse, and then A to the finite set via G, then we can consider the composite function G circle F inverse, which will also be a bijection. And we have found a bijection from B to the finite set. That gives us that B is finite. And it's sort of small, but it is what it is, and it is rigorously and properly proven that if A is finite, then so is B. We'll leave the reverse direction as an exercise and prove a similar result later on. I'm thinking about which result we should go next, because there are a few here which have some links to one another, and yet I'm thinking to myself, what's the best way to go about it? Okay, I think we're going to go in this direction, and we're gonna slowly work our way through this collection of problems on cardinality. So the next question, we're going to sort of refer to a rather annoying set that was previously defined, but we're gonna just take a little bit over here. We're gonna take a look over here. So we're gonna define for any point in the two-dimensional space, this particular set is the collection of points that satisfy a linear equation and it has connections with equivalence relations and all that good stuff, but we won't be using that at the moment. And here is the claim. The claim is that no matter which pair of points you choose, the sets that these points represent will have the same cardinality. And this is rather long and tedious and took a lot of effort the very first time that I solved it. And then one of my students came up with a really, really clever proof. And I really want to present this proof to you guys. So my student came out with this. I thought it's really clever and I'm going to present this result. So my student made a really astute observation between these two sets. Let's start with the picture, because a picture paints 1,000 words and actually sort of generates the idea for the proof. He made the observation that if we look at the set UV, it's actually the collection of points on a line. And furthermore, this line has a particular y%. So roughly speaking, we're going to get UV looking like this, and likewise for RS. Now my attempt is to sort of draw a bijection like this, where I take every point from RS and I shift it up to the point on UV, but there's a really sneaky shortcut to all of this. Here's the shortcut. What my student did was find a bijection to the real line. So this is what my student did. He first established a bijection from UV to R. And we're going to write this as a supposition. In fact, we can go one step further. He showed that there is a bijection from UV to R, which means that UV to R, or the box containing UV to R, right, they have the same cardinality. So what he did is first shown that the box containing UV has the same cardinality as R. What he then did was deduce that by the same logic, RS has the same cardinality as R. And if UV has the same cardinality as R, then R must have the same cardinality as UV. Cardinalities can swap places. So furthermore, R has the same cardinality as RS. And what my student deduced is that if UV has the same cardinality as R, and R has the same cardinality as RS, we must have that UV must have the same cardinality as RS. So that's a really clever insight there, which makes the proof really, really short. Because to prove the first statement may seem daunting, but it's actually pretty clean. But let's go ahead and conclude first. So we can conclude that UV has the same cardinality as RS. However, we first need to establish this lemma right here. We first need to establish that UV has the same cardinality as R. So let's go ahead and do just that. This is the claim, and that's a really, really clever claim because the set, or rather the box that UV represents is a straight line, and each point on this straight line has coordinates x, y, but y is given by this coordinate, right? So it's actually x, 3x plus v minus 3u, and this is the box containing UV. Remarkably, my student contended that he can biject onto the real line with just the x-coordinate. So that is going to be our proof. In fact, if we do it properly, the bijection can go both ways. So here's how we're going to prove the result. Well, to show that UV has the same cardinality as R, it's enough to show that R has the same cardinality as UV. And how we're going to do this? To show that two sets have the same cardinality, we need to find a bijection from one to the other. So we're going to define the function from R to UV by f of x equals to the point x 3x plus v minus 3u. We know that this is well defined and unique. We can do a quick check on that. To show that it is bijective, we just need to show that it is injective and surjective. Usually surjective first, so let's do surjective then injective. To show that it is surjective, we will fix a point in UV. And we will hunt for an input. Our input here is going to be the x-coordinate. So we're going to choose R in R. Then f of R is going to be equal to this point by definition, which is basically surjection, right? That's basically what it means for f to be surjective. For every output, you can find some input. And injection means for every output, you have at most one input. So we'll suppose we have two inputs. Such that the outputs are the same. We want to conclude that the inputs are the same. But if the outputs are the same, then the points must be the same. And if the 2 points are the same, then the coordinates must be the same. And you can check that in both coordinates, we will get x1 equals to x2, which means that the inputs are the same, which tells us that the function f is both surjective and injective. And we can conclude that f is a bijection. And hence, because there is a bijection from R, there's a bijection from R to UV, we can conclude that R and UV must have the same cardinality. And that's the proof. So it's a really clever proof. It takes a lot less effort than if we were to just directly prove from one line to the other. I was really impressed by this proof. And now what we can go ahead to prove, we're going to switch gears a little bit and establish several counting principles, if you would. So there is this result that seems obvious but actually takes a little bit of effort to prove, and that is the result that if you can find an injection from one set to the other, they must have the left. If you can find an injection from the inputs to the outputs, then there must be fewer inputs than outputs. Let's formulate this result properly in just a moment. So here's the claim. If we have two finite sets, and we suppose that there exists an f from A to B, an injection, exists an injection from A to B, then the number of inputs must be lesser than the number of outputs, or at least not more than the number of outputs. And this is a rather curious claim. I mean, it's pretty straightforward, like kind of obvious. But how do we prove this properly, rigorously, in a clear manner? Let's go ahead, and we're going to prove by induction. And this is what we mean by proof by induction. So we're gonna prove by induction on n. And what this means is that we're going to show that no matter how large or small the size of A is, you will still always get this result. So it might be a bit strange with the m's, but don't worry, it works out. Let's start with the base case. And in this context, the base case is n equals to 0. What does that tell us? Well, if n equals to 0, then m being a natural number means that m is definitely bigger than or equals to 0. But if n equals to 0, then m is bigger than or equals to n. So we're kind of done. There isn't really much to prove in this context. But how do we prove in the induction step? So let's go ahead to prove the induction step. Now, what does the induction step say? It says that if the size of A is equal to K, we will get this result. Then if we can find an injection, we can conclude that the sizes work out very nicely. So let's just first write down the hypothesis and see how we can use that in just a moment. We're gonna use this symbol to represent the size of B. It works out, nothing to worry there. So what does that tell us? Okay, so let's go ahead to try to prove the result more generally. So suppose n equals to k plus 1. And what it tells us is that A has the items x1 all the way to xk plus 1. And B, well, again, let's just suppose that it's y1 all the way to ym. And our goal is to show that k plus 1 is smaller than or equals to m. That's the objective of this proof. With this objective in mind, let's suppose that we have an injection. And we have our goal in mind. We want to show that k plus 1 is smaller than or equals to m. At this point in time, it's a bit strange. How do we actually go about to prove it? And perhaps we could draw a few pictures and try to make sense of this. So let's draw the pictures for A. And let's draw the pictures for B. And we know that we have an injection. We do know that we get an injection, so we can sort of draw something akin to, say, this. Sort of. Of course, the xk cannot point to anything else, otherwise it's not injective. And the idea here is almost, what if we were to sort of cancel out these two items? Here's the idea. If we can cancel out these two items, in a sense we sort of eliminate these two items, what remains is an injection from the left side to the right side. We still get an injection. But by the induction hypothesis, we will have k being smaller than or equal to the number of items on the right hand side, which gives us actually our goal. So that's sort of the idea here. We call this the cancelling away trick. In a way, you sort of cancel away the last items of the set. Now, how do we actually argue the case? Here's how we might go ahead to do it. We know that f is a function, because it's an injection, so it has to be a function. So f is a function. The input xk plus 1 has an output. And to make our arguments simpler, we're going to do a bunch of relabeling so that this output points to ym, just to make things easier. And now we have sort of the setup of our interest. We're not really concerned with all the other items, but we are interested with what we have here. Well, if f is an injection, then none of the other xi's can point to ym. If it does, we're going to get two different inputs with a single output. That's a contradiction. And so we know that that's not going to happen. So we can justify it this way. Whenever the inputs are different, the outputs must be different as well. And what that tells us is that all of the fxi's will lie inside all of the other yj's. So what's the sneaky little trick here? Here's how we're going to do it. We're going to define a new function, right? So we're going to define a new function and show that we get an injection. And ironically, we're not going to define it too differently from the existing function here. We're going to define a function g from x1 to xk to the y1s to ym's, well, m minus 1s, to be more precise. We will define the function like this by g will take any of the inputs and just throw it out into the output set according to f. I mean, we know that f works out very nicely, everything is well defined there, so why not just define gxi as fxi? After all, if f is well defined, then g will be well defined as well. It works out. But what's interesting is that because of this, we can conclude that g is an injection. In some sense, it inherits all of the properties from f, and you can check this out if you want. You can try to prove this as an exercise to check that g is an injection. But once we have g being an injection, we have an injection from a finite set to another finite set. And this time, the size here is k, right? We have k items here. Now, we do have the induction step that tells us if the input size is k, then the input space will be smaller than the output space. And this tells us that, by the induction hypothesis, that the size of the input space has to be not more than the size of the output space, but that simply gives us k plus 1 less than or equals to m as required. And that's that. It's a really clever proof of induction, I have to say. It's a really amazing proof, and I think I was really amazed and shocked that this proof happened. Yeah, I was really quite impressed by this particular proof. So this is, I believe that it has a name. It's called the pigeonhole principle, but I think there are a few iterations of the pigeonhole principle, so we're not going to use that name. But what did we prove in the end? We have proven that if there is an injection from one set to the other, then the input set is smaller or not more than the output set. It's a really cool result here, and I think that's pretty mind-blowing that we can prove it using induction. Now, what's even more mind-blowing is that there are actually multiple proofs of the other result. There's a sort of a result. There's a result for injections. There's firstly another result for surjections. And actually there are more proofs for the surjections. It's actually pretty amazing. I'm going to go with the proof that is presented in the course in which this idea is being taught. But if time permits, I might go ahead to prove it in the other manner. So do let me know in the chat and the comments if you want to see that. So we're going to prove another result. So here's a claim of, in some sense, the dual result, and that is if A and B are finite sets, and you can find a surjection from the input to the output, then the input space must be not less than the output space. That sort of makes sense. I mean, if everything goes in, then clearly we should be able to cover all grounds, and this guy should sort of be larger. We're going to prove by induction on the size of n once again. So let's go ahead. So let's start with the base case, and that is n being equal to 0. In this situation, we want to show that m equals to 0. And it's kind of hard. So we'll suppose for contradiction that m is bigger than or equals to 1, which means that b has at least one element, right? So there exists some b in b. Now let's not use b. Let's use y. There exists y in b. There is an item in b. And since f is a surjection, or technically we need to make this supposition. So suppose there exists a surjection from A to B. Then since f in this supposition is surjective, you must be able to find some item, some input in A such that f of x equals to y. And this tells us that A is minimally, well, this tells us that A is non-empty. But we assume that A had 0 elements, which means that A is empty. Which gives us a contradiction. And since we get a contradiction, we know that m cannot be more than or equals to 1. This condition gets contradicted, which means that m as a natural number can only equals to 0, which is less than or equals to n. I mean, it's equal to n, so it's less than or equals to n. That's the base case, and let's go ahead with the induction hypothesis. This is where things get a little bit tricky, but we're gonna work it out. Okay, so we'll suppose that the result is true if the size of A is equals to K. So what does that tell us? Well, we're going to sort of do a similar approach where we're going to sort of cancel out the last term, just like before. So let's go ahead to do just that. But before we do that, let's draw a picture. We probably want to draw pictures here. So let's draw the set for A. And let's draw the set for B. And here's the interesting part. We want to try to do a cancel out trick once again, but it's not entirely obvious whether or not this is gonna work. But let's just set it up first. Let's just first set this up. So we'll now, just like before, we have a function. And this time we're going to hit every single person, roughly speaking. So since f is a function, without loss of generality, we'll suppose that f of xk plus 1 equals to y of m, right? So here's the idea here. Now, it's very tempting to just strike them out and repeat the exact argument. However, we don't actually know whether the argument will still hold, the reason being that yes, we can cancel out the x1s, but could it be possible that there is some other item inside A that points to ym? Well, yes, it's entirely possible. And that's why we need to be really careful before we go ahead with the argument. And we have to think about how we might go ahead to establish this argument. So let's consider the possibilities. Is it possible that there is some other item that points to ym? Yes. And is it possible that there is no other item that points to ym? Well, that's yes too, right? That's actually a yes as well. So let's consider these possibilities. What information do we have? We can now go ahead to prove this result, and our goal is to show that k plus 1 is bigger than or equals to m. Because we want to show that if the result is true for the size of a being k, it should be true for the size of a being k plus 1. So let's go ahead with case 1. The first case is that for any xi in A, where I is equal to 1 to k, now it's excluding the last guy, f of xi is not equals to ym. In other words, such an arrow over here doesn't exist. The only item where the ym has an input, the only input that ym has is xk plus 1. In this situation, if we can have this really nice result, then we can literally apply the exact same trick. We can cancel out these two items and then observe that the remaining expression must be a surjection. We might need a bit more effort to prove this, but it's doable. So let's go ahead to establish that. So we will now define G from the remaining inputs to the remaining outputs by whatever f outputs. We know that f cannot output into ym because we are under a supposition here, so everything is well defined. And to check surjection, let's just check that G is surjective. I think we can leave it as an exercise. Can we leave it as an exercise? Nah, let's do it together. Let's do it together. It looks a little bit involved here. We're gonna fix yj inside B, right? And we know that f is a surjection. We know that f is a surjection, so since f is surjective, we can find some x, we'll call this nj in A, such that f of x and j is equal to yj. And what we do know is that this x and j cannot be equal to xk plus 1. And the reason why is this, right? So if x and j equals to xk plus 1, then yj will be equal to f of x and j equals to f of xk plus 1 equals to ym. And however, this y in B, so ym does not actually lie inside B, right? Because we purposely chose outputs from this restricted set. So it can't actually be xk plus 1. So this whole thing tells us that x and j must lie inside A, and therefore, well, I think we can do it this way. Put a bracket here. But that tells us that g of x and j equals to f of x and j equals to yj, which means that g is surjective. And since G is surjective, right? We have that G is surjective. We have a surjection from the set of size K. This tells us, and as a whole, this tells us that this set K has to be bigger than m minus 1. Because G is a surjection from a set of size K to whatever this is. So if there is a surjection and the input size is K, by the induction hypothesis, we get the conclusion we want for K. Unfortunately, that's not the only case, and we actually need to check the other case, because we've checked the case when these guys don't interfere with the ym. But what if they do? And it's entirely possible that that's the case. Let's clean up the board and go ahead to prove that case. So we've already proven that this result is true in the case when the xi's don't interfere with the yj's at all. But it is entirely possible that they do interfere. There could be some xi in A, where I is some index, it's not every index, but one of the indices, such that f of xi equals to ym. Can we prove this result? In other words, what happens if some guy interferes? Alright, so that's the question. What happens if someone interferes? Then that's important. Well, let's think about it. The idea that we have here is sort of similar to the previous case. We hopefully will show that we can still get a surjection. Okay, but it's kind of, it takes a little bit more effort this time around, but let's just take a look. So let's go ahead to prove this case. So we'll define a function from A to B in the restricted sense. We're still restricted, so in other words, this time around, we don't know if ym is gone. In fact, this time ym exists, right? There is some guy in the input space that goes to ym. This time it exists. So let's do a bit of, well, I don't think we need any relabeling. It's fine. We're gonna still restrict the input space, but the output space is gonna be untouched, right? So we'll define G from the input space to the output space by G of xi equals to f of xi. We're gonna use the same function, and let's just show that this guy is indeed surjective. And if we can show that it's surjective, then we can show what we need to show, but we'll take a look at that in just a moment. So we'll fix, here's a claim. We claim that G is surjective. So let's prove the claim. So let's go ahead. So we'll fix yj inside the output space. And we know we have a few cases, right? So if yj equals to ym, then we know that there is an input from xi into b. So then there exists xi in A such that g of xi is equal to f of xi is equal to yj. We're good to go there. But what if yj is not equals to ym? Then can we find an x, well, say x sub something else in A such that we still get the result? The answer is still yes, right? And it might not be so obvious here, but the idea is that since xk plus 1 goes to ym, right? Since xk plus 1 goes to ym, and this other item will go to ym, these items will have an input that cannot include these guys, right? Does that make sense? So because xi and xk plus 1 all point to ym, for the other yj's, you can only choose from the remaining guys in A. So if yj is not equals to ym, then, for any xi, then there exists some x, say L in A. In fact, let me write that down over here, sorry. This is not xi in A. Give me a moment. We'll call this, say, A prime. Call this A prime, just to distinguish it from the usual A. So A prime is the restricted set. So firstly, if yj is not equals to ym, then we know we still get an input, right, such that f of xl is equals to yj. Now we're gonna go one step further because this input could very well be this guy, but actually it can't be, right? So let's justify that. So if xl is equal to xk plus 1, then yj equals to f of xl is equal to f of xk plus 1 equals to ym. But we've already worked with the assumption that yj is not equals to ym. So it's a contradiction. And this implies that xl is not just in A, it's actually in the restricted set as well. If it's in A, then if it's equal to xm, if it's equal to xk, then if it's equal to xk plus 1, we get a contradiction. So it cannot be equal to xk plus 1, but everything else is in the restricted set. So xl is in A prime, which means that g of xl equals to f of xl. This is well defined, and this equals to yj as required. And so we know that g is surjective. G is surjective. It works. It just works. And since G is surjective, by the induction hypothesis, I think there's a typo here. This should be xk. The number of items in the input space has to be not less than the number of items in the output space. But that means that if you add 1 to the left side, it's even bigger, right? So you get the result. It's a really, really cool result. There is a shorter proof to this. If you're interested, do let me know if you want me to prove it. But that establishes the other case, and this establishes that if the input space, if there's a surjection from the input space to the output space, then the input space has to be not smaller than the output space. That's pretty cool. We have some names for it, but I don't think that's really crucial for our discussions. And ironically, once we have established that, we can actually go ahead to prove a really, really seemingly straightforward result, but we can use these results to help us establish that particular result. What result am I talking about? Okay, give me a moment. Let me write out the question, and we'll go ahead to prove it. So here's a claim which we can use our results to prove. Here's the claim. If A has the same cardinality as two finite sets, then the finite sets must have the same number. It's kind of strange, isn't it? Kind of obvious. Like, of course it's gonna be the situation. But we can actually use our results to prove this. So let's go ahead to prove it. And the idea works this way. Let me just draw out the idea just for everyone's benefit here. So A, you can biject this guy into the set up to m elements. And you can biject from A to the n element set. And likewise, you can do the composite function trick, if you would, which is a bijection. So here's how we convey this idea really cleanly. And that is, since A has the same cardinality as the first finite set, you can find a bijection from A to that finite set. And similarly, you can argue the same for the other finite set. And by our reasoning that we've explained many times, we can get a bijection between the finite sets. Because F is a bijection, so its inverse is a bijection. And if you take the composite of two bijections, you get another bijection. And once we get this result, what does this tell us? It tells us that the bijection is both injective and surjective. Now, since it is injective, the number of items in the input space is smaller than the number of items in the output space. And since it is surjective, the number of items in the input space is not smaller than the number of items in the output space. So if you get these two results together, we can conclude that m must be equal to n. And that's why I purposely put this question over here after we've done all of that hard work, just to show that, yeah, two sets which are finite and have the same cardinality can only have one cardinality. It's sort of redundant, but it is what it is, right? So there's that. And finally, we can look at a more stricter result from what we have proven so far. Let's first state it and prove them both. So here's our claim. Once again, we have a function, or rather we have two finite sets, A and B. A has size n and B has size m. And now we suppose that f, there is a function, or rather there is a surjection from A to B such that it is not injective. We claim that n has to be bigger than m. In other words, previously we had equality, but if you can go one step further and show that there is one guy which is not injective, then the inequality is actually strict. And here's the idea, right? The idea is that if you can go from here to here and you can find some repetition, then intuitively there should be strictly more items in the left than on the right. That's pretty cool for finite sets. Infinite sets are a little bit more tricky. We don't really have this property for infinite sets, but for finite sets, we're good to go. That's pretty cool. So how do we go about proving this result? Let's go ahead and prove it. And let's go ahead by contradiction. Let's try by contradiction here. So we'll suppose there exists f from A to B that is surjective but not injective. And we'll now suppose that n is smaller than or equals to m. Let's suppose for the sake of argument that that's the case. Now, if we do get n smaller than or equals to m, then we know that if f is a surjection from A to B, we know that n has to be bigger than or equals to m. So, since f is surjective, n is bigger than or equals to m, and this tells us that we must get n equals to m. Because in order for the two inequalities to work out, we must have an equality over here. So that's sort of the little trick that we're going to use here. And we know that f is surjective. We do know that f is surjective, so we can now assume that n equals to m, right? So for each j equals to 1 to m, we're going to take a yj and find a guy inside the input space. There exists there exists xj, let's not use xj, let's use xnj inside the input space, such that f of x and j equals to yj. Right? That's the idea here. And we are going to make a rather bold claim that f is injective, which is a violation. It's a contradiction. We assume that f was not injective, right? So here's our contradiction. So we claim that f is injective. And how do we go about with the claim? We're going to show that if two inputs are different, then the outputs must be different. And here's how we're going to go about it. So we will suppose x and 1 is not equals to, no, I shouldn't use n. I realize n is a bit confusing here. Let's just use r. I don't know why I use r, but it is what it is. Suppose xr1 is not equal to xr2. Let's just phrase it this way. Then, what do we know about fxr1 and fxr2? Well, the definition that we have here is that we will get fxr1 equals to y1 and fxr2 equals to y2, but y1 is not equals to y2. But that's sort of a weak argument because that assumes that we're choosing an XR1. We're choosing an XR1, right? So how do we sort of establish the situation? Let's salvage it. So let's first fix R1 and R2 inside the set 1, 2 to n. Right? And we now know that XR1 and XR2 must be inside of A, right? Because that's what we have over there. So since that's the situation, we'll get this result. Although there's something a bit sus about it, I need to think about this result. It's a little bit sus about this, right? So perhaps let's go back. Let's just first claim that F is injective. Okay, so let's prove this claim. So we'll try to prove it a bit more organically. So we'll fix x1 and x2 inside, well, not x1 and x2. Let's fix s1 and s2 inside A, and we'll suppose f of s1 equals to f of s2. We want to eventually show that s1 equals to s2, and how do we go about doing that? Here's how we might go about it. Then, okay, just give me a moment. I want to take a look at my notes here. It's actually a really tiring proof. Okay, perhaps I need to rephrase this thing just a bit. So let's rephrase over here. So we know that F is surjective, which means that for each j, we can find an integer in A. Well, there exists some integer rj in 1 to m, such that f of rj is equals to yj. Okay, and here is, well, not f of rj, apologies, f of xj. F of xj. Okay, f of xj. What am I doing? F of xrj. Okay, that's more like it, right? Okay, that's more like it. So we're gonna be a little bit sneaky over here and observe, and we're going to do it this way. We will define Sj to be the minimum of Rj's such that f of xrj equals to yj. Now it turns out that there's only one number over here, but by defining it this way, we definitely know that Sj, well, then f of xsj will still be equals to yj. And that's the only one that's unique. So by setting it as a minimum, we allow for it to be unique, right? It's the only possible expression here. And now here's something really, really interesting, right? So we can fix x inside A, then clearly x must be equal to xsj for some sj, right? Which means that f of x will be equal to y, j in this context. Now what's really, really interesting here is that we can now use this fact to prove that f must be injective. Because if we were to, okay, I think we got this. So now we're gonna fix two inputs, t1 and t2 in A. Then there exists, we'll say, there exists k1 and k2 in 1 to m, such that f of xk1 equals to f of xk2. Well, what am I saying? Apologies. There exists k1 and k2 so that so that t1 equals to xk1 and t2 equals to xk2. Right? xk1, xk2. And since all of these things are really well defined for us, then f of t1 equals to f of xk1, which equals to f of xk2, which equals to f of t2, or more precisely, we'll go this way. Apologies. I'm actually proving this on the spot, so this is really interesting. Okay, so I don't think we need any of these guys. I don't think we'll need this. Yes. Oh, what am I doing? Right, so there exists k1 such that, okay, what am I doing? Okay, I think we know this in the back. So if you fix t1 and t2 in A, you can find k1 and k2 such that t1 equals to x sk1 and t2 equals to x sk2. And the reason why we want this x sk1 and x sk2 is to show that f will be injective. And here's how we're gonna do it. So we're gonna suppose that f t1 equals to f of t2. What does that tell us? Then we must have f of x sk1 equals to f of x sk2. But by our definition of s sub anything, the s's must be unique. So therefore, sk1 must be equal to sk2. And if sk1 equals to sk2, this tells us that, let's end off the finale over here. This tells us that x sk1 must equal to x sk2. But that tells us that t2 equals to t1. And what that means is that if the outputs are the same and the inputs are the same, we must have that f is injective. So all of this tells us that f is injective, but that contradicts the fact that f is injective. So the real trick is right here. It's really, really, really sneaky. So it's a really sneaky result over here. Okay, so yeah, that is basically the result. That is the result. And okay, there is a little bit of a technical problem over here. So strictly speaking, how do we know that x equals to xsj for some sj? Here is the question. How do we actually know this? Okay. So this is actually the important part, which I actually haven't resolved yet. Alright? So we'll need to prove this result before we can call it a day, but we're almost there. We are almost there and we are ready to go. Okay, so let's go ahead and try to prove this result. So here's the result, and I think this is actually the really hard part of the result, because Sj is by definition the minimum of the Rj's. So let's give it a shot. So if x is in A, I have actually no idea how to prove this, so we're really going in blind today. So x is in A, which tells us that f of x lies inside y1 to ym, which means that f of x equals to yj for some j, and right, we can conclude then this tells us that f of x equals to f of s, well, xsj for some sj, and I have no idea how to go about the rest of this argument. This is kind of awkward and embarrassing. Okay, let's try this way. Suppose, okay, so we know that x must be equal to xi for some I. Since fx equals to xsj, we know that f of xi equals to f of x sj. And this tells us that I has to be bigger than or equals to sj, because sj is the minimum, right? It's the minimum of all these other guys. So I has to be bigger than sj. Now, if I is bigger than sj, then what can we derive? Oh no, I am pretty stuck over here. Not too sure how to continue from this. Oh gosh, this is rather awkward and embarrassing. Perhaps I need to go to a more rudimentary proof, but it's okay. Let's just see what we can get here. If I is bigger than sj, I would definitely like to obtain some form of a contradiction, correct? Okay. Okay. All right. We're gonna change plans here. I found a better proof which is way clearer than this. So let me clean up the board, and we're gonna reprove this properly. Okay. This is a really roundabout way. It dawned on me that, wait a minute, there is actually a result that I can use here. Okay, so let's just clean the board. We'll be back. Alright, let's return here, and we want to prove things again. And here's sort of the new strategy which I have at the back of my mind. Now we know that f is a surjection and not an injection. So that tells us that then there exists some, say, yj, or we'll do it this way, without loss of generality for ym in B after relabeling, there exist two x's that point to that yj. That points to the ym, right? You have two inputs that will point to ym because f is not an injection. The idea is to sort of eliminate one of these guys. So we will define, right? We'll define g from A, excluding, say, xj, to B by g of x equals to f of x. We'll define it this way. And when you define it this way, you can show that G is a surjection. Why? Because if you take any item in B, right, if you take any of these guys in B, if you chose ym, you can still find an item in A, xi, right? You can still find an item in A, xi. If you chose an item from here, from everything else, then your inputs definitely cannot be xj because xj already points to ym, right? So more precisely, if for yj not equals to ym, f of there exists an x in A excluding xj such that g of x equals to y of j. The reason why is because if x equals to xj, what that means is that f of x must be equal to f of xj, right? Or yeah, well, xi, xj, whichever, which equals to ym, right? Which is a contradiction. Right? Okay. So therefore, we must have a surjection. So therefore, G from A excluding xj to B is a surjection. And we can use a result previously that tells us that if we take the set on the left and we exclude xj, we're left with a set of size n minus 1, right? That has to be bigger than or equal to the size of the output space, which is m, and therefore we must have that n plus 1 is bigger than or equals to m. This is actually one of the results we proved just now, but more precisely, that tells us that does not tell us anything. Darn it. Well, that was awkward and embarrassing. That was very awkward and that was very embarrassing. Well, that's kind of awkward. M plus 1. Oh no, what am I doing? Bad algebra. That was so bad. If n minus 1 is bigger than or equals to m, then n is bigger than or equals to m plus 1. And that tells us that it's bigger than m. And we're good to go. And we can prove a similar result for injections. In fact, we're actually taking proofs that we've done before and sort of just reframing them in order to meet this current situation. So let's clean up the board and prove the parallel result for injections. So here's the parallel result for injections. We're gonna suppose that you can find a function from A to B that is injective and yet not surjective. So it looks a bit like this, right? It looks a bit like this, but it's not gonna hit everyone, right? Then n must be strictly less than m. And the proof is going to be pretty much the same as what we have done so far. So since f from A to B is not surjective without loss of generality, for the output ym, or rather, no matter which input you throw in, it cannot output ym, just without loss of generality. So we can now define G from A to B excluding ym by G of x equals to f of x. For x in A, it's well defined because none of these guys are yms. And you can check that I'll leave this as an exercise. G is an injection. Which tells us that the number of items in the input space is strictly less, or rather is not more than the number of items in the output space. So since there are a total of n items in the input space and m minus 1 items in the output space, n must be smaller than or equals to m minus 1, which means that it's smaller than m strictly. And we are done. And that is the other result for f being an injection, and we get a result of the size of the sets. That's pretty cool, I have to admit. That's pretty amazing. And that's cardinality. It definitely took a little bit more effort than the other parts, but it's a worthwhile exercise nevertheless. In the next stream, we're gonna use our ideas of cardinality to describe countability when we talk about bijections to infinite sets and some tricks that we can do with it and some of the strange, bizarre proofs that arise from it. So I'll see you guys in the next one.